Welcome to this problem walkthrough. Today, we'll dive into the problem number 1061, titled Lexicographically Smallest Equivalent String. This problem challenges us to think critically about character mappings and equivalence classes. By the end of this session, you'll have a solid understanding of how to solve it efficiently. Let's get started. In this problem, you're given two strings, S1 and S2, which are of the same length, along with another string called base str. The task revolves around understanding how characters in S1 and S2 can be considered equivalent. Specifically, two characters, X and Y, are equivalent if either they are the same character or if there exists a chain of equivalences connecting them. For example, if S1 is ABC and S2 is CDE, then A is equivalent to C, B to D, and C to E. This also means A, C, and E are interconnected and considered equivalent. The goal is to transform base str into its lexicographically smallest equivalent string by replacing each character with the smallest equivalent character in its equivalence group. Let's see how the input and constraints are structured. The output for this problem is simply the lexicographically smallest equivalent string of base str, derived by following the equivalence rules. For a better understanding, let's look at the first example. Here, S1 is Parker, S2 is Morris, and base str is parser. The output string is macaque. This output is generated by replacing each character in base str with its smallest equivalent character. To understand how this transformation is performed, we'll break it down step by step. In this example, the equivalences derived from S1 and S2 are P maps to M, M maps to O, R maps to itself, K maps to I, and E maps to S. Using these mappings, we now transform each character in base str. The character P becomes M, A becomes O, R remains R, S remains S, E becomes S, and A remains R. Combining these, the transformed string is macaque. This demonstrates how the smallest equivalent character is chosen for each position. Let's move on to another example. In the second example, S1 is hello, S2 is world, and base str is hold. The output string here is HDLD. To explain this, we first identify the equivalences, H maps to W, E maps to O, L maps to R, and O maps to L. Using these relationships, we transform base str step by step. H is replaced by W, O is replaced by L is replaced by R, and D remains D since it has no equivalence mapping. The final transformed string is HDLD. Let's consider one more example to reinforce this concept. Here, S1 is ABC, S2 is CDE, and base str is ED. The output string is OB. First, we find the equivalences, A is connected to C and E, forming the group A-C-E. Similarly, B maps to D, and C maps to E. With these equivalences, we transform base str. The first E in base str maps to the smallest character in its group, which is A. The second E also maps to A. Finally, D maps to B. Combining these, the transformed string is OB. Let's summarize the constraints and edge cases to complete the problem statement. The problem has a few key constraints to keep in mind. The lengths of S1 and S2 are between 1 and 1000, and they are always the same. The length of base str can go up to 10,000 characters. All strings consist of lowercase English letters. Some edge cases to consider include scenarios where S1 and S2 create completely disjoint equivalence groups, or when characters in base str don't appear in either S1 or S2, these characters remain unchanged. Additionally, if S1 and S2 are identical, base str will remain the same. Finally, if S1 and S2 are permutations of each other, the equivalence groups should still be formed based on the lexicographical order of characters. These constraints and edge cases ensure the problem is well defined and solvable within the input limits. To solve the problem of finding the lexicographically smallest equivalent string, one approach we could consider is the brute force method. The idea here is to create a mapping of equivalent characters by iterating through the two strings, S1 and S2. For each pair of characters at corresponding positions, we update a data structure, like a dictionary or a list, to maintain groups of equivalent characters. Once we have these equivalence groups, we can transform the base str by replacing each character with the smallest character in its equivalence group. However, this method has significant drawbacks. Searching through equivalence groups repeatedly is computationally expensive, leading to a high time complexity of O(n squared). This makes the brute force approach inefficient and unsuitable for large inputs, as it lacks scalability. A more efficient solution is to use the union find approach, also known as disjoint set union. Here, we treat each character as a node in a graph, and the pairs of characters from S1 and S2 form edges between nodes. Using union find, we can dynamically group these characters into equivalence classes. Once the groups are formed, we replace each character in base str with the smallest character in its equivalence class. The steps involve initializing a union find structure for all 26 lowercase English letters, performing union operations for each pair of characters in S1 and S2, and finding the smallest representative for each equivalence class. Finally, we use these representatives to transform base str. This approach is highly efficient, with nearly constant time complexity for each operation, thanks to techniques like path compression. It's scalable and handles large inputs well, making it a strong candidate for solving this problem. Another approach we could use involves graph traversal methods like depth-first search, DFS, or breadth-first search, BFS. In this method, we consider characters as nodes and equivalence pairs, S1, I, S2, I, as edges, forming an implicit graph. The goal is to find connected components in this graph, where each component represents an equivalence group. Using DFS or BFS, we can explore the graph and identify all connected components. Once we have these groups, we replace each character in base str with the smallest node in its corresponding component. This approach has a time complexity of O(n plus m), where n is the length of the strings and m is the number of edges. While it's efficient, it can be slightly more complex to implement than union find. Ultimately, we choose the union find approach because it efficiently tracks connected components and ensures lexicographical order through its design. This eliminates the need for explicit graph traversal, simplifying the solution. Union find stands out as the optimal strategy for several reasons. First, its nearly constant time complexity per operation ensures excellent scalability, even for large input sizes. Second, it's simpler to implement compared to graph traversal methods like DFS or BFS, which require additional data structures and explicit exploration of nodes. Additionally, union find guarantees optimal results by always choosing the smallest representative for each equivalence class, ensuring that the transformed string is lexicographically smallest. When comparing union find to brute force, the difference is stark. Union find is far more efficient and scalable. Compared to DFS or BFS, it's faster and less complex due to its optimized operations, such as path compression and union by rank. Therefore, the final strategy involves using union find to group characters dynamically, compute the smallest equivalence, and transform base str efficiently to achieve the desired result. In this problem, we are tasked with transforming a string called base str using a set of equivalence mappings defined by two other strings, S1 and S2. The relationship between the characters in S1 and S2 defines equivalence classes, where each character in S1 is equivalent to its corresponding character in S2. The objective is to replace each character in base str with the lexicographically smallest character from its equivalence class. For example, if two characters are considered equivalent, we want to ensure that any transformation uses the smaller character in terms of alphabetical order. The output is a transformed version of base str where this principle is consistently applied. Now, to solve the problem efficiently, we need a data structure that can help us manage and query these equivalence classes. The union find, or disjoint set union, DSU, is perfect for this task. It allows us to group characters into equivalence classes and quickly find the smallest representative for any given character. In this setup, each character is treated as a node in a graph, and equivalence relations are represented as edges connecting these nodes. To implement this, we start by initializing a parent array, where each character initially points to itself, and a rank array, which helps optimize the union operations by keeping the tree structure balanced. Once initialized, we can build the equivalence classes by iterating through the pairs of characters in S1 and S2 and applying the union operation. During this process, we ensure that the smaller character lexicographically becomes the root of the class. Finally, when transforming base str, we simply replace each character with the root of its equivalence class, which represents the smallest equivalent character. The union find structure is crucial for this solution because it allows us to efficiently merge and query equivalence classes. One key optimization is path compression, which flattens the tree structure during the find operation, making future queries faster. Another important detail is ensuring that when performing union operations, the smaller lexicographical character always becomes the root. This guarantees that each equivalence class is represented by the smallest possible character. We also need to carefully handle edge cases. For instance, if S1 and S2 contain identical characters, no transformations are needed as all characters already map to themselves. If S1 and S2 define overlapping equivalence classes, the algorithm properly merges these into a single class. Lastly, for characters in base str that do not appear in S1 or S2, we leave them unchanged since they are not part of any equivalence class. The two main data structures used here are the parent array and the rank array. The parent array tracks the parent node of each character, while the rank array helps maintain a balanced tree structure during union operations. This balance is important for optimizing the efficiency of the algorithm. Speaking of efficiency, let's analyze the time complexity. Union find operations are nearly constant time, specifically O, alpha, n, where alpha is the inverse Ackermann function, which grows extremely slowly. Processing the equivalences in S1 and S2 takes O, n, and transforming base str takes O, m, where m is the length of base str. Combining these, the overall time complexity is O, n plus m. In terms of space, the algorithm requires only O1 additional space beyond the input in union find arrays, making it very space efficient. Let's walk through an example to see the algorithm in action. Suppose the inputs are S1 equals ABC, S2 equals BCD, and base str equals ABCD. First, we initialize the union find structure. The parent array starts with each character pointing to itself, so it looks like A equals A, B equals B, C equals C, D equals D. Next, we build the equivalence classes. When we union A and B, it becomes the parent of B, resulting in A equals A, B equals A, C equals C, D equals D. Then, we union B and C, making A the parent of C, so the array becomes A equals A, B equals A, C equals A, D equals D. Finally, we union C and D, and A becomes the parent of D, giving us A equals A, B equals A, C equals A, D equals A. Now, to transform base str, we replace each character with its root. Since all characters map to A, the transformed string becomes AAAA. The final output is AAAA. Here, we are implementing the function smallest equivalent string, which takes three inputs, S1, S2, and base str. The goal is to determine the lexicographically smallest equivalent string based on the equivalences defined by S1 and S2. To achieve this, we use a union find data structure. First, we define a helper function find that performs path compression. This function ensures that we can efficiently find the root or parent of any character. Next, the union function is defined to merge two equivalence classes. It attaches the larger root to the smaller root to maintain lexicographical order. After that, we initialize the parent dictionary, where each character from A to Z is its own parent initially. This setup allows us to establish equivalences based on the S1 and S2 strings. For each pair of characters in S1 and S2, we call the union function to merge their equivalence classes. Finally, we begin constructing the transformed version of base str by iterating through its characters. For each character in base str, we use the find function to determine its smallest equivalent character and append this to the result list. By doing this, we ensure that each character in base str is replaced with the lexicographically smallest character from its equivalence class. Once all characters have been processed, we join the result list into a single string and return it. This gives us the transformed string where each character respects the equivalences defined by S1 and S2, ensuring the smallest lexicographical order for the result. Here, we start implementing the solution by using the union find data structure to group equivalent characters. We declare a parent map that will store the parent of each character, initializing every character from A to Z as its own parent. This helps us establish that initially, each character is in its own group. Next, we define the find function to locate the root parent of a given character. It uses path compression to optimize the structure, ensuring that all nodes in the path point directly to the root parent. This is a key step in making the union find operations efficient. Finally, we begin defining the union function, which will merge two groups while ensuring that the lexicographically smaller character becomes the parent. The comparison between root x and root e ensures that the merged structure maintains the desired ordering. In the union function, if the roots of the two characters are different, we update the parent to maintain lexicographical order. If root x is smaller, root e points to root x, otherwise, root x points to root e. After defining the union operation, we process the input strings s1 and s2. For each pair of corresponding characters, we call the union function to group them as equivalent. Finally, we construct the result by iterating over each character in base str. Using the find function, we replace each character with the smallest lexicographical equivalent from its group. The string builder is used to build the transformed string efficiently, and the final result is returned as a string. This ensures that the output is the lexicographically smallest equivalent string based on the given equivalences. To solve this problem, we start by initializing a parent dictionary where each character maps to itself, essentially creating a disjoint set data structure. This allows us to track connected components of equivalent characters. Next, we process the equivalences given in S1 and S2. For example, when processing the pair A and C, we find their current roots using the find function. Since A and C are not yet connected, and A is lexicographically smaller, we update the parent of C to point to A. Similarly, for the pair B and D, we connect B and D by making B the parent of D, as B is smaller. Lastly, for C and E, we find that the root of C is now A, so we connect E to A, making it the new root for both. This step ensures all equivalent characters are grouped under the smallest representative character in lexicographical order. After processing the equivalences, we move on to transforming the base str. For each character in base str, we use the find function to determine its smallest equivalent character. For instance, when processing the character E, we find that its root is A, so E is replaced with A. Similarly, the next E is also mapped to A. For the character D, its root is found to be B, so D is replaced with B. Combining these transformations results in the output string ob, which is the lexicographically smallest equivalent string formed from the given mappings. Now, let's consider a larger example with S1 as LeetCode, S2 as programs, and base str as source. We begin by initializing the parent dictionary to track equivalences. Then, we process the character pairs from S1 and S2. For the pair L and P, we connect them by making L the parent of P since L is smaller. Similarly, for E and R, we make E the parent of R. Continuing this process, we connect E with O, T with G, and O with R. Additionally, we connect D with A and E with M. This step ensures that all characters in the equivalence groups are linked to their smallest lexicographical representative. With the equivalences processed, we now transform base str, character by character. For S, its root is itself, so it remains S. For O, we find its root to be E, so O is replaced with E. Similarly, U remains U, as it is its own parent. For R, its root is E, so R is replaced with E. The characters C and E also remain unchanged as their roots are themselves. Combining these transformations gives the result sus, which is the smallest equivalent string based on the equivalence groups formed earlier. In this final example, we have S1 as AB, S2 as BA, and base str as ABA. We initialize the parent dictionary as before. Then, we process the equivalence pair A and B, connecting them by making A the parent of B, as A is smaller. When transforming base str, we find the root of A to be A, so the first A remains A. For B, its root is also found to be A, so B is replaced with A. Finally, the last A also maps to A. Combining these transformations results in the output string AAA, which is the lexicographically smallest equivalent string for this example. To analyze the time complexity of our solution, we can break it down into 3 key steps. First, we initialize the parent dictionary to map each of the 26 lowercase English letters to itself. Since the alphabet size is fixed, this step takes constant time, specifically O26, which simplifies to O1. Next, we process the equivalences in S1 and S2 by performing union operations for each pair of characters. Each union operation relies on the find function to determine the roots of the characters involved. The find function uses path compression, which ensures an amortized time complexity of O, alpha, n, for each call. Here, alpha, n, refers to the inverse Ackermann function, which grows extremely slowly and is considered a small constant for practical inputs. Since we perform union operations for every character pair in S1 and S2, this step takes O, n asterisk alpha, n, time, where n is the length of either S1 or S2. Finally, we transform base str by finding the smallest equivalent character for each of its characters. If base str has a length of m, this step requires O, m asterisk alpha, n, time because each lookup involves a find operation. Combining these steps allows us to quantify the time complexity of our approach. Now, let's summarize the overall time complexity by combining the contributions of all three steps. The initialization of the parent dictionary takes O1. Processing the equivalences requires O, n asterisk alpha, n, and transforming base str takes O, m asterisk alpha, n. Adding these together gives us a total time complexity of O, n asterisk alpha, n, plus m asterisk alpha, n. Since alpha, n, is effectively constant for all practical purposes, the time complexity simplifies to O, n plus m. This means that the runtime grows linearly with the combined lengths of S1, S2, and base str, making the solution highly efficient for large inputs. Next, let's examine the space complexity of the solution. The parent dictionary, which maps each character to its parent, requires storage for at most 26 key-value pairs since it covers all lowercase English letters. This is a constant amount of space, or O1. The find function, which is called recursively, can theoretically have a call stack depth proportional to the number of unique characters in the equivalence classes. However, due to path compression, the effective recursion depth is reduced to O, alpha, n, which is constant for practical input sizes. Finally, the result list, which stores the transformed base str, requires O, m, space, where m is the length of base str. These components together determine the total space complexity. The overall space complexity is O, 1 plus m, which simplifies to O, m. This reflects the constant space used by the parent dictionary and recursion stack, combined with the space needed to store the transformed base str. Comparing this to a brute force approach, the optimized solution clearly stands out. A naive method would involve iterating through equivalence groups and repeatedly checking or merging characters. Without union find, this would require O, n squared, operations for merging in O, m asterisk n, for transforming base str, leading to a total time complexity of O, n squared plus m times n. In contrast, the union find approach reduces this drastically to O, n plus m, by leveraging efficient union and find operations. Additionally, the brute force method's space complexity is also less efficient, as it lacks the fixed size optimization of the parent dictionary. Finally, let's analyze the best, average, and worst case scenarios. In the best case, all characters in S1 and S2 are already part of the same equivalence class. Here, no additional unions are needed, and the time complexity is O, n plus m, with a space complexity of O, m. In the worst case, all characters belong to distinct equivalence classes and need to be processed individually. Even in this scenario, the time complexity remains O, n asterisk alpha, n, plus m asterisk alpha, n, which simplifies to O, n plus m, due to the small value of alpha, n. The space complexity also remains O, m. This consistency across cases is supported by the mathematical proof of union find's efficiency. The amortized time complexity of union find with path compression is well established as O, alpha, n, per operation, and since alpha, n, grows slower than logarithmic functions, it is effectively constant. This ensures that the dominant terms in the problem are linear in n and m, confirming the final complexity of O, n plus m. When solving this problem, there are some common mistakes to watch out for. First, ignoring edge cases like empty strings or cases where S1 and S2 are of unequal lengths can lead to runtime errors or incorrect results. It's important to validate inputs upfront to ensure your solution handles these scenarios gracefully. Another mistake is overwriting character mappings. For example, if S1 is ABC and S2 is def, mapping A to D and then later trying to map A to E would create conflicts, rendering the solution invalid. Always check for consistency when updating mappings. Lastly, many people assume symmetry in character mappings, thinking that if A maps to B, then B must map to A. However, mappings are directional, and this assumption can lead to incorrect logic unless explicitly stated in the problem requirements. Inefficient iterations are another pitfall to avoid. For instance, checking character equivalences repeatedly in nested loops can unnecessarily increase time complexity. Instead, aim for a single traversal of the input, using auxiliary data structures to optimize the process. Another issue arises from improperly handling non-mappable characters. For example, if characters in S1 don't exist in S2 or vice versa, your solution might run into logical errors. This is especially true if the problem specifies strict one-to-one mappings. Properly accounting for such scenarios ensures your implementation is both robust and aligns with the problem constraints. In interviews, you'll want to focus on a few key areas. First, pattern recognition is critical. Many mapping problems involve concepts like equivalence classes, union-find structures, or hash maps. Be prepared to justify why you chose a particular data structure for your solution. You should also discuss trade-offs, such as time versus space complexity. For example, a union-find approach might save time but requires additional space for parent and size arrays. Testing your solution against edge cases is equally important. This includes handling empty strings, strings of different lengths, and large inputs to ensure your solution is efficient and correct. Lastly, clear communication is vital. Walk your interviewer through your thought process, particularly when designing mappings or checking equivalence, to demonstrate your problem-solving skills. On a related note, you might find it helpful to explore problems like LeetCode 205, 290, 399, and 953, as they share similar concepts and can deepen your understanding. There are also alternative approaches you can consider. One approach is using union-find, or disjoint set union, which is particularly useful for problems involving equivalence classes. This method is highly efficient, operating near O(n) with path compression, but it does require additional space for parent and size arrays. Another option is using two hash maps for bidirectional mapping, which is ideal when the mapping needs to be strict in both directions, such as ensuring A maps to B and B maps to A. While simple to implement, this method does consume extra space. Finally, sorting or transforming strings into a canonical form can be helpful for problems involving grouping or detecting equivalences, like anagrams. However, this approach may increase time complexity to O(n) log n, so it's important to weigh the trade-offs before deciding on the best method for your specific problem. Great job completing this walkthrough. To recap, we used the union-find data structure to handle equivalence classes and ensure efficiency. This problem highlights the importance of understanding transitive relationships and optimization techniques. Thanks for watching, and don't forget to like and subscribe for more coding tutorials. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!